What's up, everyone? It's me, Miss Wesley, and it's calc time once again. I'm here hanging out with my Lego constant of integration plus c. Don't want to forget about that as we solve these differential equations. And today we're going to continue with separation of variables, algebraic method to try to take an equation like the one that you see here at the bottom of page 3 of your differential equations packet. And it involves a derivative. We want to get this panned out so the x's are on one side, the y's are on the other, and we can use integration to solve for y. Couple jokes to start off the video. First one is, what is a butterfly's favorite subject in school? Well, that would have to be mathematics. And what is a bird's favorite type of math? And of course that would be algebra. Bird. Let's look at this first one. All right, so I want to star this one as having sometimes what's trickiest about these problems isn't really the calculus involved. It's not really the integral. It's the algebra that it takes to get this answer simplified. One thing we definitely do with separation of variables is we want to get the x's on the left, the y's on the right side of the equation. So this might as well be something that we move over first. We can multiply both sides by dx to get that over to the right-hand side. We want to do two things now. We want this binomial to be over on the right side, and we want this, what do we need? We need this y to be over on the left side. Let's divide both sides by y, and let's also, unless this is going to clutter it up too much, see if we can follow, let's divide both sides by x squared plus 4 to get that over to the right. So cleaning this up a tiny bit, these go away, divide to 1, you get 1 over y dy must equal x over x squared plus 4 dx. This was the point that we had, the variables are separated, x is on one side, y is on the other, perfect spot to take an integral of both sides. On the left side, looks like pretty much your run-of-the-mill 1 over y. We know that has its own special rule. We're going to have the natural log of the absolute value of y. And you'll remember from the example problems we already did that even though this has a plus c with it, we're going to save the plus c. We only really need to write it once in this equation, so we might as well write it on the right-hand side. This part is the reason I double-starred it. Looks like u substitution could come in handy with taking this integral, and now is as good a time as any to refresh it. So let's pick the more complicated part of this expression. Let's let u equal x squared plus 4. It's got a linear derivative that we'll see in a second that should cancel nicely with the x that's on top of the fraction. So if you recall the side work of u sub, we take a derivative, du dx, so just a 2x. And then, I don't know, so that I have something to plug in for dx, maybe I'll get dx all by itself. So we can sub in these two things, du over 2x. Where we see an x squared plus 4, we can write a u. Where we see a dx, we can write that fraction. Back to the integral. So we've got x up top divided by u, something that we called u. And then in for dx, du divided by 2x. Let's let these divide to 1 as well. So the x's are going to divide to 1. And then let me just transfer this over so we can see it a little bit better. We have natural log of absolute value of y equals the integral. Now I see two constants. I see 1/2, so I'll put that maybe on the outside. And then I also see a 1 over u in this expression, so 1 over u. We'll take that with respect to u. All right, so trying to be careful, still have to integrate the right-hand side. You've got natural log absolute value of y, and then speaking of natural log, it would also be the natural log of u on the other side. So it'd be natural log absolute value of u. Instead of writing u, I might just do two things at once, and I'll plug back in the x squared plus 4. X squared plus 4 that we used for the original substitution. I look at it to see if I forgot anything, and it would be embarrassing if I forgot the plus c. We need it on at least one of the sides, so we'll put it on the right-hand side. This is the bulk of the work. Now we need to make it look nice. We need to think of some algebra that we can do to get y by itself. When we saw one of these earlier, right, in previous notes, we thought, we could exponentiate both sides. We could raise e to both sides of the equation, and it would make things work out really nicely on the left-hand side of this. So I'm going to raise e to the natural log absolute value of y equals e to the 1/2 ln x squared plus 4 plus c. Okay? Now are the finishing touches. You have good news on the left side. On the left side, looks like we just have e and the log base e canceling. All you have left is basically just y. It's the absolute value of y. There was a rule that we used for this side the other day. We said if you have e to the sum of two terms, you can split it up into e to the first part times e to the second part. And some of this really simplifies nicely. There is a log rule. So now we're dipping back into our pre-calc rules we used to know. There is a log rule that says you can swing up this exponent, or swing up this coefficient, I should have said, as a power, turn it into an exponent. You can make it absolute value of y equals e to the ln of this to the 1/2. So I'll say x squared plus 4 is already positive. So let me just keep it in parentheses, to the 1/2. And then e to the c, we said this earlier too, if c is just any constant, then so is e to the c. We can just call that times c and maybe swing that out front. Since c is any positive or negative real number, you can drop the absolute value bars, make it y equals, and we'll write the c out front as a coefficient. This is e to the log base e. So actually, just like that canceling happened back here with the e and the ln, same thing gets to happen here. And we're going to leave it as x squared plus 4 to the 1/2. If this were multiple choice, you might see it as the square root, right? We know this is the same thing as saying c, and we'll say square root of x squared plus 4, and that's a really good way to leave that answer. Notice the time-consuming part, the bulk of the work wasn't calculus. We had taken antiderivatives by the time we got here, and then using those rules to try to clean it up and get y by itself was helpful. Let's look at a couple more. So at the top of page 4, you've got this one with some trig in it. So I see a y cosine x on the left side and a secant of x on the right side. First thing I usually always do is move the dx over to the right-hand side. So we can do that by multiplying. Y times the cosine of x dy now equals secant of x times dx, right, if we multiply both sides. I look over it, we got to make sure all the x's are on the right, and we don't quite have that. We need to divide both sides by cosine of x to make that happen, and this just gives you y dy. On the other side, I wonder if, dipping back into our trig knowledge, if there's a good way to rewrite this. I could think of it as, I guess secant could be like a 1 over cosine. And that's going to be divided by cosine again. So I guess I could say this is times another 1 over cosine dx. We know this, and this is a trig function that we have an antiderivative rule for. 1 over cosine is also known as secant. We kind of just use that rule. So y dy equals secant times dx. Like that. And then why write it split up like that if we could just write it more simply as secant squared of x. If the next move, now that you have the variables separated, if the next move is to integrate both sides, I'm not really worried about the left side, and I'm not worried about the right side as long as we have a rule for that, for our trig antiderivatives, and we do. On the left side, take it up a power. We'll take its integral and go y squared over 2. We'll save the plus c for the other side. Secant squared, you're thinking of a trig function that has a derivative of secant squared, and that would be tangent. Secant squared's antiderivative will be tangent of x. And then I talked about putting the plus c on the other side. Got to make sure that I remember it. So this one's going to be a little bit quicker to simplify, right? We could multiply both sides by 2 to start getting y a little bit more by itself. We said you don't really have to write 2c. If c is any constant, then 2c is also any constant, so that can just be c. And then we can, what's the last move? Take a square root of both sides. Since that is an even root, right, I got to remember there's a positive and a negative option. So y could be plus or minus the square root of tangent to tangent x plus c, depending on, maybe there's an initial condition I could plug in later to help me get c, but for now we'll leave it general. And one more. We'll look at this one with an exponential expression. So same deal. This one's a little tricky too. We got to figure out a way to get this term split up so we can get x's on one side and y's on the other. One thing I can do, I definitely am going to move the dx to the other side. I feel like that's been my first move for all these so far. So dy equals e to the x minus y, we'll have to deal with that in a second, times dx. Now I'm thinking of this. 2 problems ago, we used a rule. It was that x to the a plus b turns into the product of x to the a times x to the b. I want to use that rule here so we can get this term split into 2 to have a hope of getting the x terms on the left and leaving the y terms on the right. So I'm going to write this as dy equals e to the x times e to the negative y. I think that should do the trick. And then dx is also there. And we can divide both sides by e to the negative y. E to the negative y on the left, e to the negative y on the right. Your right side looks great, e to the x dx. This side has an e to the negative y on the bottom of the fraction. Why don't we just flip that to the top? We'll write it so that it kind of looks like the right side. It's e to the y times dy. I think now is the perfect time to integrate both sides because you have the variables separated. So we're going to take antiderivatives on the left and the right, putting the plus c on the right. Ooh, my favorite thing to integrate, e to a variable, is its own integral, right? No inside derivative to worry about here. So e to the y definitely equals, we'll say e to the x, and don't forget the plus c. Our last obligation is to try to get y by itself, to try to use some algebra. So we got to think for a second. In another scenario, we had what? What did we have? We had a natural log, and we wanted to free the y from the natural log. So we used raising e to a power. Here we have the opposite. Here we have e to a power, and we want to figure out something we could do to both sides to get that power to swing down. So now I got to think back to pre-calc, right? Yet again, if I took a log of both sides, there's a rule that says that I would be allowed to swing the power down front. Think of a y's log that you want to take, right? If there are e's involved in this question, take a natural log. Take a log base e that should help with canceling. So this is natural log of e to the y equals natural log of everything that was on the right-hand side. And then here's a really good move. We're going to swing the y down front, right? We'll have y times ln of e isn't much to think about. We could just cross that off and call it 1. And on the left side, or I should say the right side, we have natural log of e to the x plus c. So I think I just have y by itself. And is it possible I'm done? Y equals, we wanted y by itself, natural log e to the x plus c. You just got your solution to that differential equation. Okay, this is Miss Wesley signing off. Have a great rest of your day.